In this video, we're going to look at equivalent resistance, specifically how you combine a whole bunch of resistors that are in many different arrangements and think about how much total or equivalent resistance there is in a circuit. And once you've done that, you can analyze circuits that are much more complicated than either purely parallel or purely series circuits that we've looked at so far. So this is kind of the part we're going to be looking at today. How do you combine resistors in series and parallel? Continuing our things to know about circuit elements. This is what we've talked about before, but I guess just wanted to highlight things. Resistors are always on the same branch in series, series resistors are always on the same branch and must have the same current. Parallel resistors are always on different branches and must have the same voltage. Series they may have different voltages. Parallel may have different currents. You're going to have to calculate that. So when it comes to equivalent resistance, we look at something like this. So we've got an EMF voltage source there at a battery, and we've got 4 different resistors there in different arrangements. One of them is clearly in series with the battery, that R1. R5 and R7 are in series with each other. R6 is in a section parallel to the R5 and R7. And so on. But this is a compound circuit because some parts of it are in series with other parts, and then there's clearly some things that are in parallel. And so we need a way to kind of put all this together and figure out what's happening in this circuit. We already have Kirchhoff's loop and junction rules, and we're going to keep using those. And now we have Ohm's law. And the last piece is to kind of use our understanding of those to come up with a rule for what resistors do when they're added up. The fundamental idea here is that no matter how you arrange resistors, there is some amount of current coming from the battery and some amount of voltage provided by the battery that, if you were to divide those two, would give you an equivalent resistance, right? Voltage over current is kind of how we think of an ohm of resistance. And so if you knew that value, you could theoretically take out that whole circuit and place one resistor of that particular value on the battery, and the battery would behave the same. It would provide the same voltage and same amount of current. The same amount of current would flow. So that's kind of what we want to envision. Now, if you imagine something like this, 3 resistors in series, the 5 ohm, the 10 ohm, the 30 ohm, with some battery voltage. Well, we know a couple of things already. We know that the current running through all of them has to be the same, and it has to be the amount of current that left the battery. We also know that the voltage of each of them added up has to be equal to the voltage of the battery, right? That's what the loop and junction rule says. And so what we want to be able to do is think about what total resistance is there in this circuit, or equivalent resistance. We usually write it as this REQ, like a subscript EQ for equivalent. We want to find that. And so the way we're going to consider this is thinking about that definition of resistance, that it's basically the resistivity, the inherent material's resistance to electricity flow, multiplied by the length divided by the cross-sectional area. So anything in a circuit that essentially does what length does, make things longer, make the path longer, should increase resistance, and anything that sort of makes the path wider, like increasing the cross-sectional area, should decrease resistance. So we're going to start with the length piece, and that's because that's really what's happening with series circuits, right? If you add one resistor after another, it's like having a longer path to travel through. And so in the end, that's what we do with series resistors. We add up all their resistances and say the equivalent or total is the sum of all of them when they're in series. So that's 30 plus 10 plus 5, or 45 ohms. So for resistors in series, they act like they're getting longer. And so we can think of them in this way. A series of resistors 1, 2, and 3 is the same as an equivalent resistance of R1 plus R2 plus R3. So we write it this way. REQ in series is R1 plus R2 plus R3, simply the sum of the resistances. We can kind of prove this to ourselves by using the loop rule. We know the voltage of the battery is going to be equal to the voltage of each of them added up. We know from Ohm's law that I from the battery times REQ should be equal to the voltage of the battery, that I1 R1 is V1, I2 R2 is V2, I3 R3 is V3, and so on. The currents are all the same, so we can divide them out because it's a series circuit, and you end up with REQ is R1 plus R2 plus R3. So that's our sort of theoretical way of doing it, as well as our kind of conceptual way of doing it. So for resistors in parallel, we should first ask ourselves, do you think REQ will increase or decrease? Well, when we added them in series, it was like adding a longer path. Whereas when adding them parallel like this, it's kind of like giving it multiple paths. And in some ways, you can visually think of it as widening the path. So the area sort of is increasing, and that may make you think that adding resistors in parallel is going to increase the area. If A gets bigger, resistance goes down. So we can prove that this is how it behaves by using the junction rule. The junction rule tells us that the current that goes through the battery should be equal to the currents through each of those resistors on their different branches added up. We also know from Ohm's law that current can be found by taking a voltage divided by a resistance. So for the battery, it's V battery divided by REQ. For each individual resistor, it's V1 over R1, etc. The voltages are the same because this is a parallel circuit. So we can cancel out all the voltages, and you end up with 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3. So basically, you add the reciprocals of the resistances, and then you take the reciprocal to find the REQ of a parallel circuit. Right? So for example, I have a 5, 10, and 30 ohm resistor. I have 1/5 plus 1/12, 10th plus 1/30th. I'm going to have to find a common denominator, and then I get 1 over 3. That means REQ is 3 ohms. Now you, of course, can just do this in your calculator. Depending on how simple the numbers are, sometimes it's easy to find the common denominator, sometimes not, but that's the method. For resistors in parallel, REQ is always less than the individual resistance of any of the resistors, which if you know anything about adding up a bunch of reciprocals and taking the reciprocal from math, you probably could have predicted that adding them up is going to make them and then taking the reciprocal will give you something smaller than any of them. And that's a good check because that's just the way math works in this case. If you add up a third and a 10th and a 30th and then take the reciprocal of that, you will always end up with something smaller, or sorry, a fifth, a 10th, and a 30th, something smaller than either of those at the beginning. All right, so the summary. Resistors in series increases the total resistance, add them directly. Adding resistance is in parallel decreases the total resistance. So we add the reciprocals, then take the reciprocal. So what about something that's a little bit more complex? This is what we call a compound arrangement. Why? Well, because we clearly have the R2, R3, and R4 in parallel with each other. But then that section is in series with the battery and R1 and R5, right? In order to go all the way around from the battery back to the battery, you have to go through R1, then through something in that parallel section, and then back through R5. So in order to do this, we need to think about where will we start. And generally, you start the farthest from the battery or at the most complicated part. And so I'm going to start here with these 3 resistors in parallel. We can use our REQ for resistors in parallel formula, which basically says that we add up the reciprocals, then take the reciprocal. So the REQ of just this section is 10 ohms. Now, early on, it can be a helpful exercise to give yourself a big blank piece of paper and redraw this circuit with a 120 volt battery and now only 3 resistors, the 50 ohm R1, the REQ from the parallel section of 10, and the 20 ohm from R5. You don't have to, but that's a useful thing to help you think about it. So what can we know so far? Well, we know that REQ for the whole circuit is 80 ohms because that 10 ohm in the middle plus 50 plus 20 all in series gives us 80. Once we know that, we can calculate the total current for the battery, which is 1.5 amps, 120 volts divided by 80 ohms. Then we can do some interesting things. Well, we know that the current going through that battery is also the current going through R1 and R5. So 1.5 amps, 1.5 amps. Once we've done that, we can apply Ohm's law to say, well, what's V1? 75 volts, because 1.5 amps times 50 ohms is 75 volts. And we can do that for resistor 5, we get 30 volts. Well, now we can go ahead and use the loop rule, because if you go around the loop rule, we know the voltage for the battery, resistor 1, and resistor 5. So if we do any loop that includes any of those resistors in parallel, we should be able to find that they're 15 volts, because 120 volts minus 75 minus 30 is 15 left. Then they're all in parallel. If you were to color code them, they'd all be, I don't know, orange to green or something like that. They all 3 have to be 15 volts because they are in parallel with each other, same voltage. Once we have those voltages, we can go back to Ohm's law and say, well, 15 volts divided by 30 ohms is half an amp. 15 divided by 20 is 0.75 amps, and divided by 60 is 0.25 amps. And we can check with the junction rule. At that top junction, we have a current of 1.5 amps going in, half an amp going one way, 3/4 of an amp going another way, and 1/4 of an amp going the other way. That adds up to 1.5 amps. So the junction rule, the loop rule, all still apply. So when we're solving compound circuits, first you identify resistors in pure parallel or pure series and combine them, then to an equivalent resistor. Then we continue doing that until we have a single equivalent resistance for the circuit. Our compound circuit that we looked at had a parallel section and then everything was in series. So we only had to do this process twice, a parallel section, then a series section. But sometimes you can have more complex systems where you have maybe two in series that are then in parallel with something, then that's in series with another thing, and you'll have to do this multiple times. So you can always replace a group of resistors with a single resistor with equivalent resistance. And you can then use Ohm's law to look at that equivalent resistance for the whole circuit, or you can use it for individual pieces.